So I promised that we are going to get lots of topological spaces using metric spaces, and there are two steps to this. So the first of all, a very simple observation: if X is and D is a metric space, which means that X is a set, D is a distance, and this forms a metric properties. Okay, that is X is a set, and D maps X cross X to R greater than 0 equal to 0 satisfies the properties of a metric. Suppose we have this, and Y is contained in X is a subset, just a subset. Okay, then it's immediate that if I look at D restricted to Y cross Y, so this will map Y cross Y to R greater than or equal to 0 is a metric. Essentially nothing has to be proved. One just has to look at the definition of a metric and observe that they are all for all points, all pairs of points, or all triples of points in X. And if X is a subset, it will hold all the more for points, doubles of points, and triples of points in Y. Okay, so far so good. So we have lots of metric spaces. We'll see concrete examples. Let me just draw one there. That's the torus. It sits inside R2. R3 rather. R3 is a metric space, so the torus is also a metric space. But we want to make this into a topology. Okay, so topology from XD. So topology from a metric space XD. And we know how to define topologies. We know the efficient way is to define a basis. And we'll define a basis. So the definition is the topology associated to a metric space XD is, well, I'm going to put the here, we'll clarify and get caveats later. The topology with basis B. Well, what is it? We look at the balls around A of radius R for all A in X and all R positive numbers. Okay, so recall that this is the set of all points X in X such that distance between X and A is less than R. Or I could write symmetrically distance between A and X, but this whichever way one wants between these things. So what we do is we look at all balls of unit size and we look at the topology. This is exactly what we did in Euclidean space. And as we did in Euclidean space, we need a theorem. B is a basis, or rather the basis for a topology. Okay, so what? So how do we see this? First of all, union of whatever the sets, we'll call them S in B of S equals everything. In this case, it's the space X, as X in X implies that X belongs to the ball of radius around X of 1. So this is of course contained in union of well, maybe V in B. V is better notation. Okay, so every point is contained, for example, in the ball of radius 1 around itself. By the way, there may be no point as far away as 1 from X. Maybe the space is tiny, but doesn't matter. This is only an upper bound. Okay, so the easy part disposed of. The other we need another condition that tells us about intersections, and now we will use it in the useful forms. Okay, so what we have to show is the following lemma. We also need lemma. If I take two basic sets, which instead I will quantify by the centers and the radii. So given a1, a2 in x, yes, x, and r1, r2 greater than 0, and a point, or I'll quantify it for all. So given these two, what you want to talk about is the intersection of the corresponding balls, right? So for all x in the intersection of these two basic sets, BA1, R1, intersection BA2, R2, there exists a basic set. So I could instead say there exists rho greater than 0, such that ball of radius rho around x is contained in the intersection of these BA1, R1, intersection BA2, R2. And observe, this is quite a symmetric right hand side. So I just have to find rho so that it's contained in both of them. Then it's contained in the intersection. Well, how do we find it? We have to find it with a little bit of care. So let's look at our picture here. Let's draw a larger one. So here's a ball. It's assumed to be tiny, but it's drawn quite large, so we can see a picture. And here's another. And these are their centers, A1 and A2. These are not very good circles, but so what? I'm in a metric space. They need not be actual circles. And I'll take a point x here. And I want to find a tiny ball around it. Well, I notice that the distance between, if I take straight line, from, let's say, distance between from A to x, this is strictly less than R1 because x is here. And distance between A2 to x is strictly less than R2. So there's a little further room before you get out of this ball. And we'll make use of that room to draw a tiny circle around this one. So again, let's say we'll use this aqua-like color. So here we have this light blue circle. We'll draw a ball which is contained here. And this is quantitative and it's based on the triangle inequality. Okay. So note, as x belongs to, or we haven't quantified it yet. So we want to show for all f, let x belong to the B of A1, R1, intersection B of A2, R2. If this intersection is empty and there's no x, there's nothing to prove. Okay, so then let me write it symmetrically. Distance between x and AI is less than Ri for I equals 1 and 2. Okay, and so let rho be less than, or let's say choose rho. So choose rho such that 0 is less than rho and it's less than the smaller of these two quantities. For example, you could take it as half of the two quantities, the two quantities being the room we have in both cases, R1 minus D x A1 and R2 minus D x A2. So we have looked at the room here and the room here and taken the smaller of them and taken a smaller quantity. If you prefer to not have this loose statement, one can say this thing divided by 2 and observe that that satisfies these things. Okay, and then we have the claim ball around x of radius rho is contained in B AI of Ri for I equals 1, 2. And this is a basic set, hence ball of radius around x of radius rho is contained in the intersection of these two quantities. Okay, so the proof of this is an application of triangle inequality. Okay, so what do we want to show? We want to show, so let y belong to ball around x of radius rho. Then what we know is that the distance between y and x is less than the quantity rho. Okay, And you also know that rho is less than Ri minus distance between x, ai. Okay. Therefore, distance between yx is less than Ri minus distance between x and ai, this point ai. So this implies that I'm leaving some space for a reason. If I look at distance between yx plus distance between x ai, well, this is less than Ri. But by triangle inequality, we have looked at distance between y and x and ai. So distance between y and ai. Okay, so that is y belongs to the ball of around ai of radius Ri. So we picked an arbitrary point and we found that it's contained in this. It follows that this set is contained in the set BAI of Ri, and it's contained in both of these for I equals 1 and 2. So it's contained in the intersection. So the work we did in having this convenient criteria has paid off, and we see that this is actually a topology. So now we have this large class of examples, as I said. Next goal will be to look at a couple of other interesting examples of metric spaces before we return to understanding more topological concepts.